So, hi everyone. Good morning, good afternoon, good evening. Um, just a bit about me. Simon already spoke about this. So, without wasting time, let me quickly jump start. Um, I'm going to cover the basics first, considering the audience from the various background before we deep dive into the session. Um, so, what is microservices? Before we talk about microservices, we have to understand what is the current challenge and what are the monolithic applications. So for more than a couple of decades, the standard way of developing application is using monolithic architecture. That is, all the components of application are in a single code base, and the scaling and deployment of the application done as one unit. This means the application must be written in a single language with completely one tech stack, and entire global team working on different parts of the application still then have to coordinate better. Okay, this way of standard development of applications and is complex, and especially it's even becomes massive when the application has to be handled across global teams. The first of all this, the first of all, the main challenges, the coordination among team members is difficult as the code base are more tangled. Okay, and if we need to scale one particular functionality of the application, we cannot do because we need to develop the entire stack of the application together, and we have to scale it up altogether. So this means we will have higher infrastructure cost, more challenges, and the entire unit has to be compatible, and everyone have to be on their toes to support the application. And the other challenges, if we are using a third-party jar, and say if one functionality needs, let's say, version 3.6, and another functionality says needs version 1.8, then we cannot have two versions. We need to either use one way or scale up our application and fix the bugs or make it scalable to support the other version. A couple of years back, we had a log4j vulnerability, and if you remember, there was version 2.14, which was the version which found vulnerable, and they were supposed to upgrade to 2.17, if I remember it right. So the entire application has to be scaled up if we are using a log4j. And if there are any dependent jars which is making use of this particular version, then we need to work around it, either to handle those jar files separately or make it as an exclusion or come up with an innovative way and do a patch on the hack just to keep those components aside. And these all increase our turnaround time and the complexity of the application stack. And this is where all this leads to the microservices architecture. So here in microservices architecture, so we are going to break down the application into multiple smaller application. So this is like several micro applications making up the big one application. The breakdown of the application into microservices is purely dependent upon the business functionality and not by technical component. So microservice of an e-commerce or a shopping website, just for an example, let's say a product, shopping cart, or a user information, checkout and payment will all be a separate microservice components. So in terms of size, each microservices can have an isolated functionality. So one service will do one specific job. And another important criteria while you know we are working on microservices is that it's loosely coupled and independent. So we can independently deploy and scale each functionality or the services, and it gives a greater flexibility, and they can have their own versions without depending upon the other component. This makes it opening up a wider platform to support different programming languages. So if I'm going to integrate a machine learning component into my functional application, I can have it in a Python where rest of my application can still run in Java. So this makes it completely agnostic to the underlying programming languages. If one microservices goes down for whatever reason, the application is still functionable and the rest of the components can support it. Say, if the payment services have some glitch, still people can view their products, add to the shopping cart, and they can check out at a later point of time. In addition, when we design microservices, these are some of the basic characteristics and the designs of microservices, which you know we have to consider it, like the isolation part, and statelessness. So to talk about statelessness, the microservices, it's good to be have it as an idempotent. That is, if a message comes multiple times, the functional and behavior of the microservices will be good to have mimic the same output. So every time a same message replayed into a service, it will yield the same output. And event-driven makes the microservices more robust and functionable. And a lot of organizations, including from my past experience, we are heavily on event-driven. And performance-wise, this is highly scalable because we can scale up the pods, or in respect of whether you are running on a Kubernetes or any other platforms, you can independently scale up them, and you can deploy and decentralize the components. So it gives a greater flexibility. So how do microservices communicate? That normal traditional way where a lot of applications goes through the API calls. That is, if they expose a HTTPS port open, so one services can send a request and probably will wait for an acknowledgement from the other service through an endpoint. This is very common, and this is an synchronous way. That is, each component has to wait for a request and a response, and it needs to be processed. Next is the messaging broker, which we will be going to deep dive um, after this one. But just to give a high level, service one, let's say a shopping cart publishes the list of products in the cart to a messaging broker, and the consumers, like a dispatcher or something, will consume them in the sequence, or in whatever order, how we are defining it, will process that order and will dispatch it. So here the service one is not dependent on service two, how it is being processing the messages. So the role of the service one is just to publish the messages. It's done, and it will move on to its next functionality. And service two, if it is just about consuming it, it keeps on consuming and processing whatever it's intended to do. This way, it is asynchronous and event driven. And the third one is the service mesh, where there will be a sidecar container acting like a proxy service within a container along with a application service, and it will be connecting to a control panel, which is network managed, and they will be handling this communication part. And this is quite widely popular and is also used, but which one to make use of is also dependent upon the application architecture and the functionality. So what is Kafka? How it is connected to the microservices? Kafka is a messaging broker. Eventually, it was originated in a LinkedIn platform and handed over to Apache Software Foundation as an open source. It is a distributed message streaming platform, and it can handle real-time data feeds with high throughput and low latencies. And it is more preferred message broker in microservices architecture due to its robust features and ability to manage large volumes of data efficiently. And based on my experience personally, we have done handling millions of transactions every single day, and we haven't seen any single latency issues or throughputs purely from a Kafka broker perspectives. Kafka supports both publish subscriber and queuing model, which makes it more versatile for various use case scenarios. Let's take an example, right? Again, I'm sticking to the same e-commerce or shopping website. So I'm picking up two users' names in random. Let's say Adam is a confused consumer who likes to add many items to his shopping cart and then removes it and adds back a different product. So there is a sequence associated with the items he is ordering to it. In parallel, let's say John is very aware of what item he needs. He just goes and adds the item, whatever he wants, to his cart and checks out. So we have two users placing their order, and they can be processed in parallel. However, the orders items placed by Adam has to be processed in sequence because he added an item, removed it, and then added something else back. If this sequence is messed up, his product, whatever is going to get delivered, will be impacted. So in case of Adam's order, the sequence has to be maintained, and however, Adam and John orders can be processed in parallel. So this is where Kafka is, even more versatile and supports this scenario. In Kafka, we have something like partition key. So this is what we are going to go a little bit deeper here. So partition key is the one which is associated with every single message and defines in which partition they will land up with. So Kafka have two major things. One is the topic, and second is a partition. Topic is the one, it's more like a channel. And within a channel, we can have multiple partitions. If we say checkout to delivery, then that can be a topic. And within those topics, we can have multiple partitions. In this case, it can be one topic for checkout to delivery, and Adam's order and John's order can go into multiple partitions. And within the partition, we can define the partition key. This is what will guarantee the sequence. So Adam's order will go in the right sequence and will get fulfilled on the consumer side, define as long as the partition key is properly defined. So this way the sequence is guaranteed. Um, just to talk about this architecture flow, right? So here on the left hand side, you will find the producer where I listed few services. And on the right hand side, there are consumers. We can see a list of consumers taking the messages. Here, the producer is, this is an asynchronous architecture. So the role of the producer is just to publish the message, and consumers will consume and will process the message as per the functionality. Here, the producer is not waiting for an acknowledgement or anything from a consumer. The only latency is producer will get an acknowledgement from the Kafka brokers that the message has been published, and consumer will consume in whatever capacity they can. And let's say the functionality of the consumer is very massive, and then we can scale up the more consumers without impacting the producer. So here I just listed three Kafka brokers. Normally the Kafka brokers are selected in odd numbers, and the number of replications, or eventually can have all replications, or at least like n plus 1 by 2, so that you will have better replications in terms of one broker goes down. So I'm going to cover about the replications in a bit later, but let's stick to this one. So here, each broker will have all the topics. So if we have, let's say, 5 topics, all the brokers will have the 5 topics will be created on all the brokers. And each topics, let's say we have 3 partitions, then the leader for a partition will be, won't be across one particular broker. It will be divided across the brokers. This way, there is more fragmentation and it is eventually distributed. So in this example, if you can see the partition 0, broker 1 is the leader, and in broker 2, it is for the partition 2, and broker 3 is for partition 1, whereas the other brokers are replicated. This way, the one broker is not overloaded. The functionality of the broker and things are equally shared, load balanced pretty much, and they can replicate. And how many replications we need for each messages, this is again to ensure fault tolerance, we can define it. And if say one broker goes down, then the rest of the 2 brokers, as long as they are replicated, will elect a primary leader and will start supporting the functionality. And Zookeeper, as it says, it's just to ensure the Kafka brokers are connected and scaled up. Now, one producer can publish to one message, or there can be multiple producers publishing to one topic. So that's why I just captured a few services here. So the service 2, which is like considered as like 2 instances of a microservices, which can produce a message and can publish it. So this is where the scalability comes into the part. If you're going to increase the number of pods to scale up, then this will support that functionality. And same way, on the consumer side, I can have one consumer, and if I need to scale up to increase the throughput, I can scale up the consumers. And when the consumer group is unique, then the microservices in Kafka eventually goes hand in hand here. So we can divide the partitions to the different consumer threads. So the service 2A, let's say it's like the order fulfillment, can consume from partition 0 and 1, and second one can consume, the second instance can consume from partition 2. So Kafka resilience and high availability is this what we have wanted to deep dive. So it is highly fault tolerant, and there are a lot of disaster recovery strategies which we can make use of. So this is where the partition things will come into the picture. In addition, we are replicating the brokers, right? In also the clusters can also be replicated across different data centers. So how it is, before we talk about the disaster recovery, how it is fault tolerant. In general, Kafka passes the message to the disk, which ensures the data durability and also ability to reprocess them. Internally, within the cluster, we can choose the number of replications. And to make it even more replicated, we can have mirror maker or Kafka replicator. So if we have two clusters, say one sits in NAM data center and another cluster sits in EMEA or APAC data center. Now, one cluster generates a message which acts like a primary, and your disaster recovery systems is somewhere sits in a different data center. Then the mirror maker can connect these two clusters. They will be replicating the messages from one cluster to the other. And if we have some network alias, wide IPs or something, then it makes it easier. So if this cluster goes down, seamlessly it will connect to the data center cluster. This way, the microservice is completely loosely coupled from the underlying infrastructure components. And scalability wise, so there are two major things we can handle with. So first, to talk about is the vertical scaling. So vertical scaling is like adding more CPU, RAM, that is the memory, and the disk space, so that if the cluster runs slow on the underlying infrastructure components, then we can scale up them. Whereas in the horizontal scaling, we are actually adding more brokers to the cluster. So earlier we saw like a 3 broker cluster. We can make it like a 5 broker cluster or something. But the downside of this is either of this approach will, need some downtime, which will impact the functional components. And especially it depends on whether we are running on a bare metal for a vertical scaling, then it needs a reboot or it depends on the virtual machine. And something that's becoming popular in the recent time is elastic scaling. So just like how the microservices application architecture runs in a microservices environment uh, in the cloud, the infrastructure components can also run in cloud, which will enable it to scale seamlessly, adding more brokers to the cluster or having multiple clusters interconnected. This way, it reduces the downtime or literally to say theoretically 0%. So the applications will always be connected to Kafka brokers and they are all load balanced. So either of the cluster or brokers will be available to serve the components. And to talk about the utilities, I'll try to keep this short because we'll have some time for the questions. So Kafka in offers KSQL. That is, we can go and query the messages using a KSQL DB, through which we can extract some valuable insight. And normally, this is not widely used unless there is a specific use cases. And a lot of enterprise architectures normally serialize the messages over Kafka, like Google using Google Protoprof or something. In that case, this won't come handy. As long as if we are using a string or JSON serializer, this will work, where we'll be able to query using the raw language. But if it is serialized, then this won't be very efficient and it will increase the load on the brokers. Kafka Connect is like a utility tools where we can source from a different components like a database or Elasticsearch and publish the messages to Kafka, more like an utility out of the box without developing a component altogether. Control center is something very critical, because this is where we can monitor the health of the cluster. We will know how many consumers or producers, how their throughput, what is that range, and if there are any lags, we can dynamically scale up the consumer pods. So this gives, and we can even generate alerts. And if we integrated this with a microservice component, we can sense, okay, the throughputs are increasing or it's low, and that means we need to scale up more consumers to increase the throughput so the lags can be drained faster. Replicator mirror maker is the one we just covered a bit. So this is mainly for the replication across different clusters or data which might be residing in different data centers. So benefits of using Kafka in the microservices part. This is the high throughput which we were talking about. It can handle millions of transactions seamlessly. We are talking about in seconds. And in general, Kafka can have one broker in a cluster can handle 4,000 partitions. And if we are talking about a 3-node cluster, we are talking about like a 12,000 partitions. That 12,000 partitions can be across multiple topics, which makes it more robust to scale based on the application needs. And their fault tolerance and the message and durability wise, they are persisted in the hard drive. So it's easily recoverable, and it decoupled the microservice components and mainly for the real-time processing. So using the partition key, we are ordering the messaging orders, and there are all replay capabilities where we can republish the messages. On the consumer side, there is something called like a consumer offset number. So when a consumer consumes a message, it updates the offset. This way the broker knows, okay, this message has been consumed. And if we need to replay messages, obviously we can go and reset the offset to whatever number or to the beginning, and we can replay the entire messages. And in case if a consumer goes down, the broker will hold the messages as long as the consumer group name is same. And when the consumer comes up, it can start consuming the messages. So the messages are not lost, and the offsets are maintained properly. And with Kafka, we can also have the streaming processing, which is the Kafka streams, and where we can go by the window-based to aggregate the messages, or based on the rule where we need to drop certain events. This comes in handy when we want to ignore certain messages or aggregate certain events by time window. But one thing with a window-based approach is like the window should be a little smaller, because that's going to put a lot of stress on the broker, because it's constantly holding the window for the messages to handle. And if there is a high throughput messages, high volume applications, then we are increasing the complexity. Now, that being said, if there is a necessity to do that, there is a other component that's where it comes, Flink. So Apache Flink is something where it offers a big data kind of streaming. So if you are heavily dependent on streaming for a batch processing, then this is not the component where we need to build it. We can switch out to the Flink. So some tips to handle. Avoid delaying messages. Like I said, do not build the messages or have a large window for the messages to hold it across. So this will increase the stress on the broker. And Kafka is mainly for the real-time event-driven application. So stick to that part. So it was good in that case. It's not a caching solution. So there have been scenarios where I have seen people using it for caching, using a key value kind of pair. No, go for a distributed caching solutions. That could be Redis or MongoDBs or a bunch of things available based on your application needs, but it's not for Kafka. And when we talk about microservices, right, a lot of people have a dependency on database for a static data or to process the messages. It will be good to decouple them, have its own separate microservice layer, and use the Kafka to publish the messages. This way, if there are any underlying bottlenecks with your database layer where it can process only certain number of messages for insert or a trigger based on the complexities, it is decoupled and the application can still run on the caching solution. So KSQL, Kafka Streams, and Flink. So this is the part I was covering, mentioning a little bit earlier. Flink is from Apache Kafka, which is for big data streaming and analysis, which is efficient if you want to have a batch or real-time streaming, and it has its own pros and cons. So, but definitely Kafka Streams and Flink have their own use cases. Do not use Kafka Streams for analytics or holding the messages for batch processing. Instead, go for Flink. And KSQL is for querying the messages. Unless there isn't any dependency, it's not widely used. Then be mindful while defining the number of partitions and topics. So what does it mean? As I said, each broker have a limit of 4,000 partitions. And if we are creating one topic with 100 partitions, then eventually by the simple math, then we are limiting the number of topics we could create. So create a partitions and you can increase the number of partitions as there is a need for the application to scale up.